Okay, number two, we've got a couple trigonometric integrals, but the featured functions here are secant and tangent. So we have the same strategy as with sine and cosine. We want to see if we can keep back factors which would constitute a du for a u substitution. So for secant, if I let u be the secant of x, du is the secant of x tangent of x dx. And if I were to let u equal a tangent of x, the du would be secant squared of x dx. Okay, so I'm looking for factors of secant and tangent to keep back with the eye of converting what's left over to secants, or I'm looking at keeping a secant squared back with an eye of converting everything over into tangents. So let's check out this first one. Can I keep a secant tangent back and convert what's left over into secant? So if I keep a secant tangent back, I'd get secant cubed 2x, tangent to the fourth 2x, and then I'd have a secant 2x, tangent 2x dx. So that would be what I'd be thinking about keeping for the du here. And so can I convert everything that's left over into secants? And the answer is yes, because what I have left over that's not secants is an even power of tangent. I know from the Pythagorean identity, 1 plus tangent squared 2x is secant squared 2x, which means that tangent squared 2x is secant squared 2x minus 1. And this allows me to exchange any even power of tangents for an even power of secants. Tangent to the fourth, 2x, is tangent squared 2x squared, and I could write that as secant squared 2x minus 1 squared. So it is possible to do that. In this particular case, it's also possible to keep back the secant squared. Is it possible to do that and convert everything left over into tangents? Well, it turns out it is, because if you keep a secant squared back, I now get secant squared 2x, tangent to the fifth 2x, secant squared 2x dx. And once again, doing this, I have an eye towards letting u be the tangent. And is it possible to convert everything that's left over here into tangents? And the answer is yes, because whatever's not a tangent, I have an even power of secant. And so I can use this identity directly as given to convert this secant squared into 1 plus tangent squared. So it is possible to do this problem both ways. I'm going to choose this way because there's going to be less algebra involved, but I invite you in the privacy of your own home to proceed this way. You're going to get two completely different looking antiderivatives, and then for an extra challenge, you can find the constant that they're off by, right? Because any two antiderivatives of continuous functions have to be off by a constant. All right, so we're going to proceed this way. So here's the integral again. I've spared a secant squared factor from the integrand, and now I'm going to convert everything that's left over into tangents. And then I'll make the formal substitution. I'm going to let u be the tangent of 2x, so that the du is 2 secant squared 2x dx. So once again, we're picking up a factor of 2 from the chain rule, and I can make the usual adjustment so that in the land of u, this integral becomes 1/2 1 plus u squared times u to the fifth du, which is 1/2 integral u to the fifth plus u to the seventh du. The antiderivative here would be u to the sixth over sixth, but I got a 1/2 there, so that's 1/12 u to the sixth plus, I integrate this, get u to the 8th over 8. That's 1/16 u to the 8th plus c. And now since I used the substitution, u is tangent 2x, I can bring this back out. I get 1/12 tangent to the 6th 2x plus 1/16 tangent to the 8th 2x plus c. And that's going to be my final answer for part A. Okay, looking at part B, I've got the integral of tangent to the 5th 2x dx. And if I want to use the technique used in part A, I'd have to be keeping back a secant tangent or a secant squared, and I don't have any secants at all. So if I just have a bunch of tangents and I need some secants, I can go ahead and convert some tangents to secants using the Pythagorean identity. I know that 1 plus tangent squared of 2x is secant squared of 2x, which means that tangent squared of 2x is secant squared of 2x minus 1. So, keeping that in mind, I'm going to peel off tangent squared, leaving me with tangent cubed, and convert the tangent squared into secants. Now I distribute through and I have two integrals. I've got the integral of tangent cubed 2x times secant squared 2x dx minus the integral now of tangent cubed 2x dx. Now this first integral, believe it or not, is a Calc 1 integral. I can let u be tangent of 2x, so the du is more or less secant squared 2x dx. I need that 2 from the chain rule that's going to pop out. And so in the land of u, what I have for the first integral is 1/2 integral u cubed du, which gives me 1/8 u to the 4th. So for this first term, I'm all set. It's going to be 1/8 tangent to the 4th 2x. Now, what do I do with this integral? Well, once again, I've got tangent, power of tangent all by itself. I'm going to convert some of those tangents to secant squareds. So I can think of this integral as being the integral of tangent 2x tangent squared 2x dx, which is the integral tangent 2x times secant squared 2x minus 1 dx. So if I break this up, I'm going to have minus, because I'm subtracting the integral tangent 2x secant squared 2x and then remember I'm subtracting here, so I subtract the negative, that gives me a positive tangent 2x dx. So I've got 1/8 tangent to the 4th 2x. What's going to happen here? The same thing that happened before. I'm going to let u be tangent 2x. This is going to give me the form 1/2 integral u du. Same substitution as before. I integrate that. I'm going to get 1/4 u squared so 1/4 tangent squared 2x plus the integral of tangent of 2x, and that's a formula we know from chapter 5. So that's 1/2 natural log absolute value secant 2x plus c. Alright, so for my final answer here, the integral of tangent to the 5th of 2x dx, after a couple exchanges of tangents for secants, is 1/8 tangent to the 4th 2x minus 1/4 tangent squared 2x plus 1/2 natural log absolute value secant 2x plus c. So that'll do it for part B, and that'll do it for checkpoint quiz 8.